So let's, first of all, you're going to have homework due Wednesday, which includes a web work that I posted on Friday, and then another web work that I will post after class today. Okay? So, and all that stuff is fair game for the exam Friday. So now, when it comes to the exam, if you go to exam prep and homework solutions, a new area that I made. So there's a couple posts here. The first one is Exam 1, Friday, February 5th. And it has a outline of, and some resources, and an outline of some guidance for studying. So the first thing is, number 1, review outline. That's the fourth one here. Review outline is a bullet point list of things that you should understand and know how to do. So that first week and a half, meaning of integral, super important. Lots of questions on that. There's an overview. Go back, watch the videos, study your notes, rework the homework, okay? It's all about the fundamental theorem of calculus, which is crucial, obviously, right? It's the fundamental theorem of calculus, so we have to know it inside and out. You will be tested on that, okay? Techniques for integration, that's what we've been doing since then. And then we'll do improper integrals today and Wednesday. Okay, so that's the review outline. The next thing is practice integral problems. Okay, if you click on that one.
Mark,
yeah.
On the outline, you posted the table integrals, whatever. So are you going to post?
Yeah.
Are you going to put those on?
Yeah, you'd have to have the table formulas. Yep. If you have to do any table integral type on the exam, you'll be given those table formulas. Okay. So on the test 1 review, this is a bunch of practice problems. Okay. Lots of just integrals, all different types, right? So there's this final skill of now that we've learned all these techniques, can you come to an integral and figure out which technique you're going to use? So you need practice at that. So these are all jumbled together. They're in no particular order. And you have that practice. And then there's a second page of practice problems, some multiple choice. I did say on here, there are some here that you're not responsible for. That may change, okay? And I'll finalize that on Wednesday. So that list of some of those questions that you wouldn't have to be responsible for the exam, that is in flux, okay? But for now, that's what the list is. The last thing is formulas. Okay, in terms of derivative rules, none will be given, okay? So in terms of knowing your derivatives, there won't be any given. You don't need to know arcsecant or arccosecant, all right? Derivatives or antiderivatives or arcsecant, arccosecant won't be on there, okay? But anything else is fair game. As far as the identities, so I'm going to kind of meet you halfway on the identities. This is what I'm going to do. The cover of the exam is going to look like this. There's going to be this on the cover of the exam. And so the first thing you'll do is you will fill this out, finish the identities, and then you'll have them for the exam. So, and then I'll give you 1% bonus for doing that. Okay? So I'm not giving them to you, but you'll have, if you just learn this sheet and learn how to fill these out, which shouldn't take you more than 10 or 15 minutes, then you'll start the exam by filling it out, and then you'll have all the identities for the exam, and I'll give you 1% bonus, okay? So there's a blank practice version that looks just like, and then I posted the completed version right below it. Okay, there's the completed version posted, and then the blank version, which you will have on the front of your exam. And you'll just do that, write them down, take a minute to do that, 2 minutes, and then you'll have them all for the exam. Make sense? And so that's all explained right here. If it's all correct, you get 1% added to your exam score. Okay, then below that post, I've posted written homework solutions for the insect. That was the first one. Then the falling meteor, and then the border elevation problem. So they've got, so you can look at solutions for all that written homework. And then as far as web work, all that will remain up all semester, and then it's after the due date, so you have access to the answers. You should be able to see the answers. So all the web work just remains posted. Okay, and so we will start the exam at 8:45. We'll come in here, and then we'll go until hopefully 10:15. So you have an hour and a half, which would be plenty of time, but some of you will want all that time. Okay, so 8:45 we'll be here Friday, and then we'll stay and collect the exams at 10:15. Any questions? Okay, as far as the web work that's already posted, some of those are change the variables, and some of those you can use the table in the back of your book in the appendix. Okay, so it's kind of a matter of figuring out which are which. Some will be both. So in order to use the table, you'll start with a change of variables, like the example we did at the end of class Friday. Okay, but we're not going to spend any more time on those. So if you need extra help, you got office hours all day tomorrow. Okay, office hours all day tomorrow. Find the assistance that you need. So make sure you're working on that at the latest tonight, so you can get help tomorrow. Any questions about homework or the exam Friday? Okay, so let's move on. Let's talk about what's called improper integrals. Not to be confused with indefinite integrals. Indefinite integrals have no limits of integration. And so for an indefinite integral, rather than getting an amount of change or an amount of accumulation, you get like a change or the quantity function, right? So when you do an indefinite integral, you're getting a quantity function. Now, an improper integral has to do with this kind of thing. All right, so consider a rate of change function that is always positive. Okay, for example, a population that grows by about 2,000 people per year. So imagine it's a city or a nation, and it's growing about 2,000 people per year. All right? What would the long-term result be to the quantity, right? So we're keeping track of. We got rate of change functions and we got quantity functions. We know that's a big part of the fundamental theorem, knowing the difference between those two. What will happen if the population has this rate indefinitely? What will the long-term result be to that quantity if you have a rate of change of 2,000 people per year? Can you imagine that? It's an important idea to think about. So just year after year, about 2,000 more people added to this nation's population or city's population. So what, in the long run, what will happen to the population? It'll get big. That was well said, right? It will get big. The population will grow infinitely large because 2,000 people is added every year for an ongoing number of years. Should make sense. So let's see the graphs. What graph am I showing you here? Rate of change. Rate of change is constant at 2,000, meaning every year the rate of change is 2,000 per year. And so what will the quantity, can you imagine what the quantity functions graph will look like? Quantities functions graph. Draw it with your finger. Draw it with your finger. Something like this. And so if we let years just go on and on and on and on, this is the improper part. Improper means we're going to consider just indefinitely. What's going to happen to the quantity? What's that? Yeah, it's just going to get really infinitely large. So if we let the number of years kind of get very, very large, then our population is just going to get very, very large. Okay, so that in mind. What would, for that, let's go back. So can you set up a mathematical expression? Can you set up a mathematical expression that represents this situation? Can you set up a mathematical expression that represents all this situation, like trying to calculate the value of the population a long, long time in the future? So could you set up an expression trying to calculate the size of the population a long, long time in the future? And so what did I give you? I gave you the rate function. I gave you the rate function, and I'm asking you for an amount of a quantity, right? So what kind of expression is that? Everyone, pretend it's a quiz. You've got to write down an expression that gives the total population over many, many years in the future, given a rate of 2,000 people per year. Pretend it's a quiz. Everyone write it down. Oh. Okay, so let's see how we did on the quiz, quote-unquote quiz. How many people wrote down integral? How many people wrote down integral? You're given a rate, you want the total amount of a quantity. This is an integral. So you should have integral. Integral of what? 2,000 is our rate function. And then you could have dt or dx, but you need to have something. Okay, and so if we're talking about starting at some point in time and then indefinitely into the future, it would be like from 0 to what? Infinity. So this is the idea of that. This is the idea of that at a rate of 2,000, what's the total growth of the population if you just let it go? If you just let it go. And what will this be? Yeah, so this will get very large. Okay, so I have another one. Questions on that? Okay, suppose the rate function is 1 over x cubed. Okay, what can you say about that rate function? What can you say about that rate function that's similar to our previous example? So I want to investigate, say, starting at year 1 or minute 1 and looking all the way to infinity of this. So how is that rate function similar to the one we had before? If I'm looking starting at 1 to infinity. Is it always positive? Yeah, it's always positive, right? So here's my rate of change function, r. So the rate is always positive. That's a 3. Okay, so if the rate is always positive, what does that mean? It means we're always continually adding on to the amount. Just like before, the population was added on 2,000 every year. Well, so 1 over x cubed is just a changing rate, but it's positive, so we're adding on, right? We're at every unit, we're adding on to the quantity. So what's the quantity going to do? Increase, decrease, or stay the same? It's a positive rate, so the quantity is always going to increase and continue to increase. So what about this integral? What will the total amount of the quantity be, starting at 1 and then just letting it go indefinitely? Infinity. Will be infinity. Let's do the math and show it. Okay, so last time, with 2,000, it's clear. We'll just keep adding 2,000 forever. That's clear. But let's just do the math and see what happens here. So, how do we do this? The first thing is, we can't plug in infinity. We have to first change this to a limit. So we're going to take the limit as a approaches infinity of 1 to a. So when we have these improper integrals, we're really looking at limits. We're really looking at limits. So this is the limit as a approaches infinity. Integral from 1 to a, 1 over x cubed dx. Okay, this should be an easy, so we've learned all these techniques for integration, and this is an easy one. You don't even need a technique. We should just know what this is. Antiderivative of 1 over x cubed. Is negative x to the negative 2. But we also need 1/2, right? So negative 1/2 x to the minus 2. Is that the right antiderivative? So we got it? Okay, and then I'm going to evaluate that from 1 to a. So I'm going to keep my limit out here, taking the limit as a goes to infinity, and I'm going to do what? I'm going to change this back to negative 1 over 2x squared. So it's going to be negative 1 over 2x squared from 1 to a. Is it fair? And so I'm going to get negative 1 over 2a squared minus negative 1 over 2 times 1 squared. And now I'm ready to, so I do all the math right. I got the right antiderivative. I plugged in my a, I plugged in my 1, and I subtracted. So now I'm going to take the limit as a approaches infinity of this expression. So when a gets very, very large, what about negative 1 over 2a squared? What's that limit? Should know that that's 0. So as a gets very, very, very large, 1 over 2a squared is going to essentially be 0 for very, very large a. And then what about this? This doesn't care what a does. It's always what? 1/2. Okay, so how about our hypothesis? Because this rate was always positive, we continually are increasing, our quantity is continually increasing all the way indefinitely. And we thought maybe that meant the quantity would just grow to infinity. Did it? No, it didn't even make it to 1. Look, we can let that rate continue indefinitely at a positive rate, and essentially the total amount of the quantity is 1/2. So what's going on here? Does it make sense? Why does it make sense? You're nodding your head. What's that? Yeah, but the rate was positive for infinity. That means we kept adding to the quantity. We keep adding to the quantity. So shouldn't it be infinity? Shouldn't the amount grow to, like the population example, right? We had a positive rate. We just kept adding more and more to the population, so it's just growing indefinitely. Same thing here. We have a positive rate. We keep adding to the quantity. We're only getting 1/2 as the total amount of the quantity indefinitely. What does your computer say? What do you think? Say, what's that? Okay, so look at this rate function. It's growing, but that positive value is what? Getting very, very close to 0. So it keeps growing by a less and less and less amount, so that essentially for large values of x, you're hardly adding anything at all. And you're adding such a small amount eventually that it doesn't, the quantity levels off, right? The amount of the quantity, instead of just growing indefinitely, it levels off. And then so the total amount of the quantity in the end is virtually 1/2. Okay? So if the rate is positive, it's like the jury's still out. Like some positive rates will keep growing the quantity indefinitely. But some positive rates, if they get small enough, will result in a finite amount, even though you're adding indefinitely into the future. You're adding you just keep adding and adding and adding according to your rate. For as large of x as you want, your quantity still levels out. It's because of the nature of that rate function, getting very, very small. Okay, so I want you to then try this. What if the rate function was 1/x? So new example. So if the rate function is 1/x, is the rate always positive? Does it get really, really small for large x? So what's going to happen? Is this amount of the quantity going to be a finite amount? Is it going to level off? Or is it going to increase indefinitely? Like the population problem I gave you. All right, we'll check it mathematically, all right? So you do the math. So now change the rate from 1/x cubed to 1/x. And let's see what happens. See what happens. Go. So put on that algebra problem on hold for a second. I'm going to go back to the x cubed. I got two graphs here, okay? So I want you to make sense of these two graphs. So get a partner, and we said the rate function was 1 over x cubed. And what happened? We said that if we accumulated at that rate starting at 1 and looked at the total amount of the quantity indefinitely, that the total amount of the quantity would eventually equal 1/2. So can you make sense of those graphs in light of what we did with 1 over x cubed? So take a second and talk about those graphs. What are you looking at? What's that graph? What's that graph? What's going on? Go. Okay, so the rate is always positive, but the rate does what? Gets really close to 0, right? So that if we tracked how much of the quantity we had starting at 1, what happens? It goes up fast at first, but then as that rate's getting really small, it's already getting really small by, let's look at 7. By the time you get to x equals 7, the rate is 0.003. And that's only x equals 7. We're talking about going to infinity, right? So by the time it gets to 7, it's only 0.003. And so what kind of addition to this quantity are we getting now? So for very, very small positive rate, yes, the quantity is increasing in value, but by minute amounts. So that what? So that it levels off at 1/2. So if we took this out to, this is our quantity function over here. If I took this out to, say, even just 100, so x equals 100, not even very big yet. Look at the amount, by now, at 100, the amount is 0.501, basically, 0.501 at 100. How is that greater than 0.5? Why is that greater than 0.5? Help me out here. What did I do wrong? Do you guys know why it's greater than 0.5? I guess. I didn't make a mistake here, did I? Okay, anyway, it's supposed to be a little bit less than 0.5. I'm not sure why it's a little bit greater than 0.5, but it should be a little bit less than 0.5 because as we keep increasing in x, it should be getting just essentially 0.5. So maybe the numerical method that my program is using has got some error, and so it's showing greater. But it should be a little less than 0.5 here, and just approaching 0.5. So what happened when you did it for 1 over x? Again, 1 over x is always positive and gets very small. What happened to the total amount of the quantity indefinitely? All right, well, we know it should increase, right? Starting from 1, it should increase. Is it finite or infinite? So let's zoom out here on the x-axis and see. Does it level off or not? Oh, we thought it might there for a second, but look what happens. So now I'm in the tens of thousands. Is it leveling off? No. Just when we thought we understood what was going on, right? Another curveball. Okay? So it's going. So what's going on in this one? I thought it's going to 0, so the rate's going to get really, really, really small, right? So why doesn't the amount of the quantity level off like 1 over x cubed? Let me graph 1 over x cubed here along with it. So the red one is 1 over x cubed. The purple one is 1 over x. Why doesn't, if your rate of change function is y over x, 1 over x, what could be the reason that we're not getting a finite amount of the quantity at infinity, even though 1 over x gets really, really small? What could be the reason that it doesn't level off? It just grows indefinitely. Yeah? What's that? Okay. Okay, so that's why the numbers work out, but why? Why? Look at the two rate functions. What's that? Okay, as opposed to 1 over x. Picture tells the story here. So 1 over x gets small in terms of the rate gets small, but not small enough fast enough. Not small enough fast enough. Do you see that it's staying much higher than 1 over x cubed? So that the overall effect, yes, it gets really, really small in the long run, but not fast enough for the quantity to level off. Okay? Because it's getting down more slowly, the quantity just increases indefinitely, like our population example at the beginning. So what does it take for this integral to converge? So just this right here like this. Say any number, say a or b to infinity rate when does this equal a finite value? What has to be true, first of all? The rate function has to. So what if the rate function is like this? There's my rate function. There's a new function, the black one. Is the quantity going to be finite or infinite? Clearly infinite, because you keep adding that same amount every unit of x indefinitely, like the population example. So what has to be true for it to be a finite amount? If we're gonna total up this quantity on and on and on, what has to be true? First of all, the rate has to do what? It has to get to 0, right? Or it has to get very small, like 1 over x cubed or 1 over x. But not only does it have to get it has to get very small. It has to get very small fast enough. So just the fact that it gets very small is not enough, because we saw 1 over x, that gets small, right? That rate of change gets very, very close to 0. But because it takes longer to get there, the quantity is infinite. Whereas 1 over x cubed gets to 0, but much faster. That's the red one. It's getting much faster, much smaller, much faster. All right, so where's the cutoff? What functions get there fast enough? So just getting to 0 is not enough. They got to get to 0 fast enough for a quantity to level off and be finite. So what is fast enough? So let's see what fast enough is. You should have found that 1 over x. This should agree with what you got for 1 over x. Natural log, the limit of the natural log as x goes to infinity is infinity. So let's just do a generic case here. And let's do this. So let's do, say, from 1 to infinity, we'll do 1 over x to the p. So for what values of p does the rate function get down there fast enough to give us a finite value, and what values of p is it too slow, like 1 over x? Okay, so here we go. We're just going to do it generically and figure out what it has to be. So we have the limit as a goes to infinity, 1 over a. So the antiderivative is, what will it be? It'll be, so we're going to see that as x to the minus p. That's our rate function, right? So when we do the power rule, it'd be x to the minus p plus 1. But then we need 1 over negative p plus 1, right? Okay, well, we'll yes, right, but we'll see that when we do the math, okay? So do I have the antiderivative correct? So I'm going to take 1 over x to the p is the same as x to the minus p. So the power rule says add 1, and then we need that 1 over negative p plus 1 when we take the derivative, okay? So that's going to be from 1 to a. So we're going to plug, and so let's do this. 1 over negative p plus 1. And what is this? This is 1 over that. So it's going to be easier to see if we do 1 over x to the p minus 1. So x to the p, negative p plus 1 is the same as 1 over x to the p minus 1. Just a rule of exponents. Change the sign of the exponent to move it down. Are we okay? 1 to a. All right, so here we go. So it's going to be 1 over negative a plus 1 times, no, p is a constant, x gets the a, 1 over a to the p minus 1 minus that whole thing with 1 plugged in. Check my work. How did I do? Plug in a for x, plug in 1 for x. Okay, so what it comes down to is this will be finite when this limit exists. All right, so we'll be in good shape when that limit exists, right? If that limit, the limit as a goes to infinity of 1 over a to the p minus 1, if that limit exists, it's not infinite and does not exist, then we're in good shape. So let's pick that apart. The limit as a goes to infinity of 1 over a to the p minus 1. Really, what we really want to know is when is that 0, right? When is that equal to 0? Okay, so when does, do this in red, we basically have this scenario. The limit as n goes to infinity of 1 over n to the r. What does r have to be for that limit to be 0? What does r have to be? It has to be greater than 0. So any r value greater than 0 makes that limit 1 over n to the r equal to 0. So what is our r in this case? That's our p minus 1. Therefore, p has to be, if p minus 1 is greater than 0, then p has to be greater than 1. Okay, so this tells us, so when p is greater than 1, that limit that I've highlighted in blue is 0, and we get a finite value. We get a finite value for the amount of the quantity that accumulates over indefinitely, right? In the long run. So in our first example, what was the value of p? What was the value of p? 3, right? It was 1 over x cubed. So p was 3, and we saw indeed that we got the total amount was 1/2. What was the p in the second example? 1. Look, not greater than 1. So that's the cutoff, is 1. As long as your exponent is a hair bigger than 1, the rate will get down fast enough for the quantity to level off. But starting at 1, starting at p equals 1, or like a fraction, p equals 1/2 or 0.9 or 0.8, then your quantity is going to grow indefinitely. The rate will, yes, the rate will get down to 0, but not fast enough if p is 1 or less than 1. And the quantity will grow indefinitely, or be what we call divergent. So p greater than 1 is called, we call that convergent. You get a finite amount of the quantity. Okay? If p is 1 or less than 1, then the integral is divergent, meaning the quantity just gets infinitely large. Okay, so this principle is really important in terms of understanding just the basics. So I could just give you lots of improper integral problems, and so you figure out which ones are divergent, which ones are convergent. That's all good, but I really want to take the time to understand what's going on, thinking in terms of rate functions and the amount of quantity that you get. When does that quantity finite, even though you're integrating for very large x? When is it finite? When the rate function goes to 0 and gets to 0 fast enough. So for this form, 1 over x to the p, that happens when p is greater than 1. Those rate functions get to 0, and they get to 0 fast enough for the quantity to converge to a value. Now there's a whole, this is a very narrow, though, family of functions, 1 over x to the p. So the example I wanted to do next was this. We don't have time. Say negative x e to the x looking from, say, but looking at from negative infinity to negative 1. So we can have improper integrals. They're considering all x values in the negative territory. So this graph of the rate function looks like this. So if you think of it going to negative infinity, it's going to 0. So the question is, does it get to 0 fast enough in negative territory for the quantity to converge? So maybe there's one in the homework like this, I'm not sure. But You're going to do the math. So it's not of the form 1 over x to the p. So you have to do the math. You have to do the math. If you get a finite value when you do that integral, then it's convergent. It got to 0 fast enough. The rate got to 0 fast enough for a finite value of the quantity. If you get infinite or a divergent integral, then that's what it is. And it got to 0 but not fast enough. So you have, if it's not 1 over x to the p, you got to do the math. In fact, evaluate the integral to answer the question. Hey, remember, I'm going to post another web work due Wednesday, so you have 2 sets due Wednesday morning.